first I want to talk a little bit about right-angled triangles. Given an angle inside of our right-angled triangle, we're going to call it theta. Theta here is not going to be the 90-degree angle, but it's going to be one of the other two. We're going to label the three sides of our triangle in a particular way. The side that is right beside the vertex of our angle is going to be called the adjacent side of our triangle. The other leg of our triangle is going to be called the opposite side. And finally, the side that's across from our 90-degree angle is always called the hypotenuse of our triangle. It's important here before we move on to note that if I put theta over here, then the opposite and the adjacent side switch places in our picture, but the hypotenuse stays the same. So the way we label opposite and adjacent does depend on where we put theta inside of our right-angled triangle. Just to illustrate that point, I want to give you an example here where I've moved the triangle around a little bit and I put theta in a different spot, and we're going to label our sides as opposite, adjacent, and hypotenuse. The easiest one to label first is the hypotenuse. It's always across from your 90-degree angle. Next, you want to use the placement of theta to tell you where the opposite and adjacent sides are. The adjacent side is going to be the one closest to the value of theta, and the opposite side is going to be the one across from the value of theta. We say that two right-angled triangles are similar triangles if their side lengths are proportional. So what I've done here is I've drawn two triangles, a bigger one in black with side lengths capital A, capital B, and capital C. And I have a nested smaller blue right triangle here with side lengths little a, little b, and little c. These two right triangles are proportional if we can create the following equalities. If I compare the side lengths A and B of my smaller blue triangle, this should be equal to, in proportion, the ratio of capital A to capital B in the big triangle. And the same is true if I replace A and B with any other two letters. So, for example, I could compare A and C to capital A and capital C, or I could compare little b and little c to capital B and capital C as well. Now, the big idea for trigonometry is that when we have similar triangles, no matter how big these similar right triangles are, they're always going to be in the same proportion. So I've assigned some values here to our blue and black triangle. I've assigned the blue triangle the edges 3, 4, and 5. And for our larger triangle, we're going to assume that this is maybe 10 times bigger than the smaller one, so the side lengths are 30, 40, and 50. So let's take a look at three ratios that we can create from our right-angled triangle. I'm going to specifically start with the larger of the two triangles. So first I want to, using theta here as our vantage point, think about the ratio opposite over adjacent. Well, the opposite side of theta is 30, and the adjacent side of theta is 40. So we're going to get the ratio here, 30 over 40, which is simplified to 3 over 4. Next, if we look at the opposite over the hypotenuse, that's going to be 30 over 50, and that's going to simplify to 3 over 5. Finally, if we look at adjacent over hypotenuse, that's going to be 40 over 50, and if we simplify this, we're going to get 4/5. Let's repeat this process for the smaller of the two triangles. Once again, let's use the same theta as our vantage point. First, we're going to look at opposite over adjacent. Opposite is a side length of 3, and the adjacent side length has a distance of 4. So when we go to create this ratio, we're going to get 3 over 4. Next, if we want opposite over hypotenuse, that's going to be 3 over 5. And finally, if we want adjacent over hypotenuse, that's going to be 4 over 5. And notice that these are the exact same ratios we got for the larger triangle. So this shows us that these ratios, these three special ratios, only depend on the value of theta that we're using. It's this idea of no matter how big our similar triangle is, as long as the value of theta remains constant, the ratios stay the same, that leads us to the idea of trigonometry for right triangles. What we're going to do on this slide is define 6 different functions from the 6 different ratios that we can form from our reference angle theta. The first one is called sine of theta, and sine of theta refers to the ratio of the opposite side over the hypotenuse. The next one is called the cosine of theta, and the cosine of theta refers to the ratio of the adjacent side over the hypotenuse. And the third one is called the tan of theta, and the tan of theta deals with the ratio of the opposite side over the adjacent side. We can also take each of these three ratios that we have and find the reciprocal of them, and those are three new trigonometric functions as well. So if we were to take opposite over hypotenuse and switch that ratio so that we have hypotenuse over opposite, this refers to the trigonometric ratio of cosecant. And the short form of cosecant is CSC. If we take adjacent over hypotenuse and take the reciprocal of that ratio to get hypotenuse over adjacent, we call this ratio the secant of theta, and it's shortened to SEC. And finally, if we take the tan ratio and find the reciprocal so that we're looking at the adjacent over the opposite, this ratio is called the cotangent ratio, or COT of theta. In this example, we're going to find the 6 trigonometric ratios using the reference angle theta given in this triangle here. Let's begin with sine of theta. Remember, sine of theta is opposite over hypotenuse, and the opposite from our reference angle theta is going to be the value of 12. So here, opposite over hypotenuse is going to give us 12 over 13. Next up, cosine of theta is adjacent over hypotenuse. The adjacent length is 5, and we know the hypotenuse is 13. Tan of theta is opposite over adjacent. The length of the opposite side is 12, and the length of the adjacent side is 5. So these are our three main trigonometric ratios. So let's move on to our other three trigonometric ratios. Our first one is cosecant of theta. Remember that cosecant is technically the reciprocal of the sine function. So cosecant here is going to be 1 over sine theta, which is 13 over 12. Next we have secant of theta. Secant theta is the reciprocal function of the cosine function. And if we take the reciprocal of cosine, we get 13 over 5 as our ratio. Next is the cotan of theta. And this is the reciprocal of the tan function. And if we take the reciprocal of 12 over 5, we get 5 over 12. Next, let's look at an example where we have to find the 6 trigonometric ratios if we're given one of the ratios off the bat. So here we know that sine of theta is equal to 1 over the square root of 2. So we have to find the other 5 trigonometric ratios. But first, we have to use this information given to us to draw a triangle. So let's go ahead and draw a right-angled triangle. And let's put our reference angle in theta. And we know that sine of theta is equal to 1 over root 2. Well, sine of theta is opposite over hypotenuse. So it must be that the length of this side is 1, and the length of our hypotenuse is the square root of 2. And now it's up to us to figure out what the length of our third side is, and we can use Pythagoras' theorem to do this. So we're given the hypotenuse, which is c. So we know that root 2 squared plus 1 squared should be equal to our missing side length squared. So this tells us a squared plus 1 is equal to 2, or that a squared is equal to 1. And solving for a, we could get plus or minus 1 here, but since we're dealing with a positive distance on a triangle, we're going to take just the positive root here. So our missing side length must also be a value of 1. With this third side found, now we can go ahead and find cosine and tangent of theta. Cosine is adjacent over hypotenuse, which is also going to be 1 over the square root of 2. And tan of theta is opposite over adjacent, which is going to give us a ratio of 1 over 1. And for our other three ratios, we can simply flip the existing ratios or find the reciprocal of the ones we already have. So sine of theta is going to tell us that cosecant of theta must be the square root of 2. And this is similar for secant of theta, it must be the square root of 2. And cotan is going to give us a ratio of 1 over 1 again, or just the value of 1. Some trigonometric ratios come up so often that we're going to need special strategies just to evaluate these particular trigonometric ratios. The first one I want to talk about is for a reference angle of 45 degrees, or pi by 4. The idea here is if we take a square where all side lengths are equal to 1, and we know that all of our angles are also 90 degrees, we could cut this down the diagonal, and by doing this we create a hypotenuse for a right-angled triangle down here that's equal to the square root of 2. So I'll let you prove that by using the Pythagorean theorem. It's also possible to note here that this reference angle down here is 45 degrees, or pi by 4 radians. That's because it's exactly half of our original angle, which was 90 degrees. So sometimes this special triangle is called the 1, 1, root 2 triangle, and it's used to find the trigonometric ratios for pi by 4 or 45 degrees. So let's go ahead and find our three major trigonometric ratios for 45 degrees. We have that sine of pi by 4 is going to be opposite over hypotenuse, so we get 1 over root 2. For cosine, cosine is going to be adjacent over hypotenuse, which again is going to be 1 over root 2. Of course, both of these measures can be written equivalently as the square root of 2 over 2. And lastly, the tan of 45 degrees, or tangent of 45 degrees, is going to be opposite over adjacent, which gives us 1 over 1, or just the number 1. Another triangle that's going to be useful for us to know is what's called the 1, 2, root 3 triangle. And we can create this triangle from looking at an equilateral triangle where we have all side lengths equal to 2. Now in this case, all of our angles are going to be 60 degrees because this is an equilateral triangle. So we're going to take 180 degrees and divide it up into 3 equal portions. And to create the 1, 2, root 3 triangle, we're actually going to slice this triangle in half. Now the hypotenuse is going to stay as a measure of 2. This leg down here is going to be a measure of 1 because we have taken this length and divided it in half. This angle in here is going to be 30 degrees, or pi by 6, because it should be half of 60 degrees. And this angle down here is going to be 60 degrees, or pi by 3. Now I'm going to draw this triangle just a little bit bigger so we can use it to get at the trigonometric ratios for 30 degrees and 60 degrees. What I'd like you to try is showing that the missing side length over here is going to be the square root of 3. So here you can use the Pythagorean theorem to show that. Sine of pi by 6 is going to be opposite over our hypotenuse. That's going to give us a ratio of 1/2. Cosine of pi by 6 is going to be the adjacent side over the hypotenuse, or root 3 over 2. And the tangent of pi by 6 is going to be the opposite side over the adjacent side, or 1 over root 3. And if you rationalize the denominator here, you'll get root 3 over 3. So that's another way of writing 1 over root 3. Next, using the reference angle of pi by 3, let's find these three ratios. First, sine of pi by 3 is going to be the opposite side over the hypotenuse side, which is root 3 over 2. For cosine, we're going to have the adjacent side over the hypotenuse side, which is 1/2. And for tan of pi by 3, we're going to have the opposite side over the adjacent side. That'll give us square root of 3. Let's use our special triangles that we created on the last couple slides to evaluate the following trigonometric expressions. First, let's work with our 1, 1, root 2 triangle. So I'm going to jot that down here for us. So 1, 1, square root of 2, and our reference angle on the inside is 45 degrees, or pi by 4. Let's say first that we want to find the secant of our reference angle 45 degrees. Well, secant is 1 over cosine of 45 degrees, and cosine is adjacent over hypotenuse. So the secant must be hypotenuse over adjacent. The hypotenuse here is the square root of 2, and the adjacent side is going to be 1. So secant of 45 degrees is going to be square root of 2. Next, let's look at cotangent of pi by 4, or 45 degrees. this is going to be 1 over tan, and tan is opposite over adjacent. So cotangent is going to be adjacent over opposite, and in this case we get a ratio of 1. Next up, let's work with our 1, 2, root 3 triangle, so let's jot that one down. And for me, how I remember what values go in as the angles is 1 is the smallest length of any of the sides of this triangle. So that means that the angle of 30 degrees, or pi by 6, must be over here. And that leaves us with pi by 3 up top, or 60 degrees. Okay, let's look at cosecant of pi by 6. Well, cosecant is 1 over sine, and sine is opposite over hypotenuse. So that means our cosecant ratio is going to be the hypotenuse over the opposite. The hypotenuse in this case is 2, and the opposite is 1, for an overall ratio of 2. Next, let's look at cotan of pi by 3. We know tan is opposite over adjacent, so cotan is going to be adjacent over opposite, just like it was above. And using pi by 3 as our reference, we have the adjacent side is 1, and the opposite side is square root of 3. So we could write this down as root 3 over 3. All right, my little epsilons, stay positive.